Everybody see that? Thank you. Okay, I'm really grateful that Raj has invited me to speak to you all this evening. I promise to not take too much of your time, but one of the things that I'd like to do is try to introduce in a little bit greater depth the exciting technology that Novavax has been developing for the manufacture of vaccines, and which we're bringing to our collaboration and joint venture with our colleagues at CPLB. As Raj said, I'm the Chief Medical Officer at Novavax. I participate in the conceptualization of some of our vaccines, as well as, in particular, the clinical testing of them. Now, so Novavax uses what we call a recombinant nanoparticle technology to induce robust immunity to a number of different diseases, including difficult problems. And influenza is, although the vaccine works, a difficult immunization problem. When we need it, we also use an adjuvant system, which we've acquired from a Swedish company by the name of Matrix M, and that can dramatically increase the magnitude of our immune responses as well as spread their specificity. And that helps us deal with some particularly difficult problems, such as avian influenza, and we'll talk about that in a moment. We have clinical development programs that address two important respiratory vaccines, influenza that has already been spoken about, as well as respiratory syncytial virus, which is a second respiratory virus that really follows hot on the heels of influenza in the elderly in terms of causing disease, and in point of fact, in the very youngest children far outstrips influenza in terms of an important pathogen. We have programs to develop both seasonal and avian influenza vaccines to address pandemics, and we also have active research in Ebola and Middle Eastern respiratory syndrome, as well as several other pipeline programs. One of the pieces of evidence that we're proudest of is in one of those other respiratory virus programs where we recently announced the first ever evidence of a vaccine to be efficacious against respiratory syncytial virus. We've also published proof of principle in immunizing mothers to protect their infants against RSV. And we have made public data about the ability of our vaccines to respond to two other tough nut problems, both avian influenza and most recently Ebola virus. We have clinical development activities, that's my area. We also have good manufacturing practices, capacities, and a very strong product development department, which interacts very closely with our colleagues at Cadilla on a more than weekly basis. Oops. So, you've already heard a brief discussion of how the VLP / nanoparticle technology works. Basically, based in basic research about the key protective antigenic epitopes in whatever pathogen we care to address. We select the genes that specify those epitopes. We make them synthetically, so we do not deal with pathogens at all. The genes of importance are made synthetically, purified, and then they're cloned into baculovirus. You've already heard about baculovirus. It's an insect virus. It's totally benign in terms of mammalian hosts. You can inject 10 to the 9th, 10 to the 10th viable baculovirus into an animal, or in point of fact, into a human, and nothing happens. You get a small immune response to it, but there's no disease. The virus does not persist. It can infect cells for one round, but it doesn't replicate. and it's cleared. What baculovirus does, and it's a huge DNA virus that can accommodate large genes, is very efficiently infect insect cells. And we use insect cells that are isolated from the ovary of the fall armyworm and grow them in tissue culture. They're a long-established cell line now that has been around being used for protein production since the 1970s. But they do very efficiently express antigens, which are encoded in recombinant baculovirus, and those antigens can be either extracted from the cells as single molecules, or the cells can be allowed to produce virus-like particles, which are essentially fake viruses. And those particles are purified by various methods depending on the vaccine and injected. As you see in the cartoon below, we go from the cloned genes to production of the recombinant baculovirus to infection of cells, and those cells produce the vaccine antigen. The vaccine antigens fall into two groups, and it really depends on whether we want to target a single protein to produce our vaccine, or to target multiple proteins. So, for example, on the left here, we have the example of the recombinant nanoparticles that we use for RSV and for Ebola. Those really consist of one protein. The proteins are made in the insect cells in their native conformation. They tend to sit and not really go anywhere. They sit in the insect cells until we harvest the cells and we lyse them with detergent. The proteins are then purified, and as we take away the detergent, the hydrophobic ends of the proteins, the tails that would stick in the cell membrane, come together because they're fatty and hydrophobic, and they coalesce right around a little droplet of detergent in the middle, which holds them all together, and you get these little rosettes of antigen, which you can see in the lower electron micrograph. The important thing about those is that the proteins sit in exactly the same conformation that they do if this was a real virus. And unlike proteins that have been made, say, in mammalian cells or in eggs, they're folded in a way that they expose a number of the antigens that would normally not be in a vaccine. And so we get some very unusual and important immune responses to those. The other kind of vaccine that we make, and this is represented by the Cadilla influenza vaccine, is virus-like particles. And we use this approach when we have more than one antigen of interest. So we encode actually 3 influenza proteins into the baculovirus: hemagglutinin and neuraminidase, both of which are well-characterized surface antigens of the influenza virus, and both of which can cause protective immune responses. We add to that a matrix protein, which is one of the internal structural proteins of the influenza virus. And that causes the cells to produce what are, in effect, influenza viruses. They express hemagglutinin and neuraminidase on their surface as little studs sticking out. And a scaffolding structure is formed by the matrix M1 protein that's wrapped in membrane, and these structures bud off from the cells and form the particles that you see in the electron micrograph on the right, yes, I guess if you're looking at it. So again, we have the correct three-dimensional display of the target virus proteins, the hemagglutinin and neuraminidase, and we have these multimeric particles that look for all the world like an influenza virus. The important difference is that they contain no influenza genome at all, and any remaining nucleic acid there is chewed up by chemical treatment with beta-propiolactone, which is a small molecule that hydrolyzes nucleic acids. So even though they look like viruses, these particles are totally non-infectious. They can't replicate. They contain no infectious influenza virus. They contain no infectious baculovirus. Now, I'm using an example here of RSV to show you how these nanoparticles and or the VLPs reveal neutralizing epitopes. Back in the 1980s, a researcher at the US FDA named Judy Beeler discovered that on the RSV F protein, this is the respiratory syncytial virus, there are 3 key neutralizing sites. And she discovered them by taking the virus, grinding it up, making monoclonal antibodies to it, and looking to see whether each particular monoclonal antibody could neutralize RSVF. Many of them neutralize RSV virus. Many of them didn't, but groups of about 3 of them did, and she used those to characterize antigenic sites on the surface of the RSV virus, and particularly on the RSVF protein. You can see a diagram here of the RSVF protein. You can see where the sites are on the 3-dimensional structure. Most importantly, if you look at the data plot now, you'll see the ability to evoke antibodies to those sites. And the green squares are, or green symbols, are symbols that reflect the serum of subjects, healthy adults, who have not received vaccine, either before receiving vaccine or before and after receiving placebo. And what you'll see that although we've all been exposed to RSV many, many times during our lives, we don't have any of these important neutralizing antibodies. However, after individuals have been exposed to the RSVF vaccine, as you can see in the red symbols, neutralizing antibodies to all 3 sites, site 1, site 2, and site 4, appear. And that's very unique. That's a response that doesn't happen in response to natural vaccination to RSV, or natural exposure, to RSV. And it correlates with the fact that although we've had, each of us, RSV many times in our lives, we're not immune to it. We continue to get it again and again. And RSV uses this strategy as well as the antigenic drift that influenza uses to evade our immunity. So here we have a way of actually having an immune response which is better than the one that nature gives us. Similarly, some of those epitopes are hard to see in flu, although they're there. Universal epitopes that can have an impact on multiple strains of flu. And we've actually mapped epitopes on the flu virus, which we respond to ordinarily, and which we respond to whether we receive an immunization with standard flu vaccine or whether we get an influenza infection. And the mapping of those epitopes you can see on the left with a non-adjuvanted H7N9 vaccine. These are the same common epitopes that we respond to if we have an infection or if we have a standard non-adjuvanted vaccine. If we use an adjuvant, our adjuvant called Matrix M, other adjuvants will do the same thing, you get additional responses to the red epitopes that you can see on the right, many of which are also neutralizing and also have broadening activity, so that our immune responses are not narrowly targeted to one strain of flu, but rather give spread responses that cross-react with many other related strains of flu. So We have, in collaboration with Cadilla, been using this technology to produce influenza vaccines. Here's a classic display of responses to our influenza vaccine, our VLP-based vaccine, and it's compared to a standard vaccine. And you may say, well, okay, it's the same as pink. It's a good vaccine. Nothing makes it special. But there are particular virtues, and Dr. Cole has already mentioned some of them with regard to this system. But the most important one is time, okay? In the last several years, twice in the last 3 years, the seasonal influenza vaccine has been much less effective than it should have been. And on both occasions, either the wrong virus, the wrong guess was made based on the preceding epidemiologic data. The wrong guess was made in terms of what virus to put in the vaccine. And in another case, the virus mutated or drifted before our very eyes during the season. The reason that's a problem is because current influenza vaccine manufacturing technologies have a long lead time. You've seen that alluded to. It can take anywhere from 6 to 9 months to produce an influenza vaccine in response to the recommendations for a given year. So once you've made a commitment to a strain, you're stuck with it. That's what you have to make for that year. And so, for example, in 2014, it became apparent as early as April of 2014 that the vaccine had the wrong H3N2 virus strain in it. While the world was being progressively infected with another H3N2 strain, for which the vaccine was poorly protective. And in some cases, that vaccine had basically zero efficacy against the H3N2 virus. But we were stuck with it because it takes 6 to 9 months to change those strains. Another challenge for speed is the possibility of avian pandemic viruses. We've seen over the years the rumbling threat of H5N1 viruses, which are avian viruses that have leapt into humans. They infect humans relatively poorly. They're not well transmitted between humans, which is lucky because they're extremely highly pathogenic. Similarly, in 2013, we saw the appearance of AH7N9 viruses, another avian virus, which caused great concern with an outbreak of infections in China. Now, in the modern world, or I should say historically, the spread of avian and pandemic viruses has occurred, but it's occurred slowly. It's evolved over months, even a year, because of simple transport. But we live in a world now in which I could be incubating influenza over several days. I've been in London and in India in that period of time, and I could be coughing on people and transmitting that virus to them all within a week. So when one of these pandemic or avian threat viruses evolves as a threat, we have to be able to respond. And because the technology, the VLP technology, is based on synthetic genes, we can respond as soon as that gene is sequenced. This is the timeline, and I won't walk you through it, for Novavax's response to H7N9. As you can see, we got the information about the gene, which was published on the 31st of March, and we were able to ship human-ready product on the 28th of June. So that's a 3-month timeline rather than 6 to 9 months. We can do this in response to seasonal vaccines as well. The H7N9 viruses are incredibly difficult to immunize against. You can see in the green what you can achieve even with very substantial doses without an adjuvant. But because we have the availability of adjuvant, you can see you can get the much larger responses that are diagrammed on the right side and can achieve those with as little as 4 micrograms of antigen, where ordinarily you would need 15 in a seasonal vaccine. To show you again, I said there were 2 components. There's the there's the hemagglutinin, there's also the neuraminidase. These are responses to the neuraminidase. Most people don't measure these, but you can see again that there's a very substantial response to the adjuvanted vaccine, and at very low doses, as low as 4 micrograms. So bit by bit, the Novavax nanoparticle and VLP technologies are proving effective in a number of difficult diseases. I show you, as a way of closing, 2 unique bits of data here. On the left, you see the world's first ever evidence of an efficacious vaccine against RSV. And on the right, the ability to provide 100% protection against experimental animals against 1,000 lethal doses of Ebola virus. We look forward to producing exactly the same kind of data regarding influenza, and in going forward and producing these innovative vaccines in collaboration with our joint venture partners at Cadila. And I think, because I'm spending your time, I'll stop there. Thank you.